Hey there students, so welcome to part 1 of the improper integral type 2 clip. In this clip we're going to be talking about the improper integrals where we are dealing with infinite discontinuities, okay? So basically we have a situation where we have an infinite discontinuity or vertical asymptote on the domain of integration. Alright, so let's go ahead and divvy up the scenario into two broad cases. There are three types of indefinite um, improper integrals involving infinite discontinuities. The first two can be classified into the area of endpoint discontinuity. So let's write that down. Endpoint discontinuity. Discontinuity. Now this basically happens where when you have the vertical asymptote or the infinite discontinuity at one of the endpoints. Okay, so it could be on the left. Case one, let's say it's at the left. If it's on the left, then this is the formula that we're going to use. So on the left side, if the function, let's say function f of x is continuous, continuous on an interval a b, then the integral from a to b of f of x dx equals the limit. Now let's take a look at what's happening before we complete this formula real quick. You notice that this is an interval that's discontinuous on an endpoint, namely a. A is open, so a is not included. All right. So how on earth can we take the integral if a is not included? So what we're going to do is we're going to make use of limits, right? We can get infinitely close to a and see what we get as an integral. All right. So what we're going to do is we're going to pick a value. Let's say c, and we're going to approach a uh, from we're going to approach a from the right, okay? Because we know that this is the left endpoint or the lower endpoint of the interval of integration. So we're going to approach it from the right of the integral. Now we're going to replace a with that c value, which is what the limit, what we chose the limit to start from, all the way to b of f of x dx. Okay, so just to give you a visual of the scenario, let's consider the following curve. Okay, I'm going to make a bounded a convergence situation here, but the case is not always convergent. Okay, sometimes it could diverge. All right, so let's say we have some function of this nature. Okay, and this function has an infinite discontinuity, let's see, on a, and this is a right here. So this function gets arbitrarily close to a, but never actually gets there. So let me draw my curve again. So let's say it looks something like this. So it gets really close and it has an infinite discontinuity there. All right, and let's say this is a and this is b, and what we're trying to do is we're trying to find the area under the curve. Let's say this is f of x from a to b. Okay, so since we can never get to a since it's an infinite discontinuity, what we're going to do is we're going to remember to the left of a. If you're approaching a from here, this is basically a from the left, and if you're approaching a from the right, this is a from the right. Okay, so what we're going to do is we're going to let c pick a value c somewhere in here, and then we're going to let the c approach a from the right. Okay, so that will tell us what the area is. All right, we're going to keep getting arbitrarily closer and closer and closer to a. Even though we don't get there, the area might have a limit. Okay, notice how as we get closer and closer, the additional units of area keeps getting smaller and smaller and smaller. So if the limit converges, then the area or this integral exists. If the limit doesn't exist, that basically tells you that the area diverges. Okay. All right, the next scenario under endpoint discontinuity, you might have guessed, is a right. What if we have an infinite discontinuity or vertical asymptote on the right endpoint of our domain of integration? So in that case, if f of x is continuous um, on the interval a, b. Okay, so this tells you that b is not included. We have an asymptote. We're going to be having an asymptote here. Then the integral from a to b of f of x dx is going to be what? Now, what do you think it is going to be? Well, it's going to be exactly like this. The only difference is we're going to switch. C is not going to approach b, but since b is the upper bound of our domain of integration, C will have to approach b from the left. Okay? So it's going to be the limit as C approaches b from the left of the integral from a to c. So we just replace b with c, and it will take the limit as c gets really close to b, because we can never actually get to b, of the function f of x dx. Okay? So let's give ourselves a visual as to what on earth this means. So consider the following scenario. This is just a random example. And the task is to find the integral under some curve from a. Let's say this is a from a to b. Okay? And let's say our graph looks something like this. And we have an asymptote on b. Okay? Pardon my curve. So let's say we have an asymptote on b right here. The graph gets really close to b without actually touching it. So let's say we have an asymptote there. So how do we do this? Since we never get to b, and we want to calculate the area from a all the way to here, all we just have to do, we know that this is b from the left, this is b on the left side, and this is b on the right side. So we're going to take a c value, and we're going to let that c value approach b from the left. Okay, it gets arbitrarily close to b, and the question is, if that happens, what happens to this area? Okay, if that limit converges, then the integral has a value, and that value is the area. But if the limit diverges, then the integral doesn't have a value. This area here is unbounded, or is basically divergent. All right, so this is the right endpoint scenario, where your right endpoint is the infinite discontinuity of the vertical asymptote, and you have to approach it from the left. Okay? All right, so that's our two endpoint scenarios. The other one is interior discontinuity. Okay? So that vertical asymptote we talked about could be at the endpoint, but it could also be in the interior. Okay? So let's write that down. Interior discontinuity. In this case, our domain of integration has an infinite discontinuity within it, okay, as opposed to at the end. All right, so there's only one scenario there, which is case number 3, and this is interior. So for case number 3, what do we do when we have a discontinuity on the interior? So this is a scenario. You write it as follows: if f of x is continuous on this interval a to c union c to b, you notice here that the infinite discontinuity I speak of, or the vertical asymptotes, is within my domain, okay, of integration. I'm going to be integrating from a to b. The break is at c. Okay, so if I have this scenario, then the integral from a to b of f of x dx is going to be what? What do you assume it's going to be? Well, we have to take a break at the center. So we're going to divvy this up into a combination of the left and the right hand situation that we considered up here. Okay, so this case right here that we have first is the right, and then this is the left. Okay, so this, when I say right, I'm talking about this right here. Okay, so you see the interval from a to b, b not included, a included. Well, that's here. So we're going to apply the right endpoint scenario here, and we're going to apply the left endpoint scenario here. Okay, this is a combination of both of them. It's not anything new, actually. Okay, so what we're going to do is we're going to integrate from a to c of f of x dx, and then we're going to add it to the integral on the other side of the discontinuity, which is from c to b of f of x dx. Okay, all right, since these two are improper integrals with infinite discontinuities, then what we're gonna do is we're gonna apply the two cases I just talked about up here. Okay. So this one is gonna be. So what I'm doing right now in most books, this is where they stop. I just want to show you additional layer just to review what we covered previously. Okay. So in this case, the upper bound is not included. C. So what we're gonna do here is we're gonna take the limit as D approaches C from the left, okay, because there's a right endpoint that is continuous here of the integral from A to D. So replace your, where the infinite discontinuity is, you replace it with a variable and take the limit as that variable approaches the discontinuity of f of x dx. This is applying the formula on the right endpoint that we talked about, plus, and then here I have to take a limit again, because in this case, the lower limit of integration is discontinuous. We have an infinite discontinuity there. So as D approaches, this is the lower bound or the left side, we're going to approach it from the right. As approaches C from the right of the integral from D, replace where the discontinuity is with the new variable, to B of f of x dx. Okay? So this is basically how we have it. So either you do the case one or case two, or you do a combination of both. All right. So let's give ourselves a visual to understand what on earth this looks like. So let's say we have uh, something of this nature. So there goes your y-axis, there goes the x-axis, and you have a function. I'm going to try my best. Let me draw the asymptote first. So let's say we have an asymptote right here, and the asymptote is on C. And the function looks like this. Say the function looks something like this. Really close, and then it curves out. And the other one really close. And then or what? Let me try that again. Sorry about that. So close and then curves out. That's even worse. It's easier to draw this by, I'll draw all this stuff by hand. Anyway, so let's say you curve something like this. Okay? So let's say we are calculating let's say this is A right here, this is A, and this is C, and this is B. So we're looking for an integral under the curve from here to here. Obviously, we can clearly see that there's a discontinuity in the interior right here. So what we have to do is this is the part of the right piece right here. We have to have D approach C from the right, from the left. Okay, so D basically approaches C from the left. So that tells you the area here. Hopefully it converges. If it converges, then we know that this whole area under the curve might converge, but we have to do this piece also. All right, so on the right side, we're going to have D approach C from the right, because we know this is C from the left and this is C from the right, and that gives you this area right here. So if this converges and this converges, then the integral exists, the limit exists, and the integral is the value of that limit. But if any one of these diverge, then the whole entire area diverges, and the integral, the area does not really exist. It doesn't have a value. Okay? All right, so there you have it. All right, so I'm going to go ahead and let's take a look at an example. Let's consider the following. So example one, go ahead and write this down. Evaluate. I want to evaluate integral from 2 to 3 of dx over x minus 2. Okay? All right, this is a pretty straightforward one. So if we examine this integral, which is a good practice when evaluating integrals, we notice that we have a scenario where we have a discontinuity. Wait, let me change the limit here. Let's go from, yeah, that's right. Okay, so we have a discontinuity at 2. Okay, so we have a discontinuity at 2. So that means that the lower limit of integration, there's a discontinuity there, so this is an improper integral. So let's give ourselves a visual so we can know exactly what we're dealing with here, okay, and what direction we're going to use. So let's say we're going from 2 all the way to 3, okay? We're going from here to there. All right, so What does that mean? Since we can't attain this value, we can get arbitrarily close. So we're going to be approaching, this is the right side of 2, right? So we're going to be having our C approach 2 from the right side, okay? C is going to be getting arbitrarily close to 2 from the right side, all right? So that's what we're going to be doing here, approaching 2 from the right. So what we're going to do is we're going to take the limit as C approaches 2 from the right, because it's the lower bound or the left endpoint that has a discontinuity of the integral from C. In order to replace 2 with that value that we're going to have the limit approach. Okay, so C to 3 of, let's rewrite this as 1 over x minus 2 dx. Okay, so there you have it. All right, so what I'm going to do is let me do the evaluate this integral on the right here, and then when I get to the step of applying the fundamental theorem of calculus part 2, I'll come right back. I'll bring it right back here. Okay, so let's split it apart, evaluate the integral, and then put it back into the limit. Okay. All right. So what we're doing is we're going to find the antiderivative from c to 3 of 1 over x minus 2 dx. Okay. I know some of you are really smart. You can do this in your head, but I just want to go over all the basic procedures. Okay. All right. So I'm going to use a u substitution here. I'm going to let u be x minus 2, and du is going to be dx. Okay, so what we're doing is we're looking for the antiderivative from c to 3 of 1 over u du. All right, so remember the formula for integrating 1 over u is a natural logarithm, right? The natural logarithm of the absolute value of u. So the rule is the integral of 1 over x dx equals ln of the absolute value of x plus c. So this is basically the integration formula I'm going to be applying here. So the antiderivative of 1 over ln u is going to be the integral from c to 3 of the natural logarithm of ln u. Oh wait, I'm sorry. Let me rewrite that. So it's going to be the natural logarithm of the absolute value of u evaluated from c to 3. Since I didn't change my limits of integration, let me change u back to what it was before, which is x minus 2. So it's going to be ln, natural logarithm of the absolute value of x minus 2, evaluated from c to 3. Okay, so this is your integration piece. Now what I'm going to do is I'm going to put this right back into my problem. So we're going to be taking the limit as c approaches 2 from the right of the natural logarithm of x minus 2 evaluated from c to 3. Okay. All right. So applying FTC2, we're going to plug in the limits of integration and find out the difference. So we're going to have the limit is the limit as c approaches 2 from the right of the natural logarithm of plugging the upper limit of integration, which is 3 minus 2 minus the natural logarithm of plugging the lower limit of integration, c minus 2. Okay. All right. So we're going to take the limit of this entire expression right here. So if I look at this one, ln of 3 minus 2, let's just bring down the limits. C approaches 2 from the right of the natural logarithm of absolute value of 1 minus the natural logarithm of the absolute value of c minus 2. Now we're going to take the limit of these two term by term. Since this is independent of of c, the limit of this is just natural logarithm of 1. Natural logarithm of 1 is 0, right? So we're going to have 0 minus the limit as c approaches 2 from the right of the natural logarithm of c minus 2. So I can plug in 2 from the right into my substitute this value into my natural logarithm. So I'm going to have 0 minus the natural logarithm of the absolute value of 2 from the right minus 2. So we're going to have 0 minus the natural logarithm. 2 from the right minus 2, you're going to have a really, really small positive number. Okay? So the question is, what is the natural logarithm of a really, really small positive number? To answer this question, it's beneficial to take a look at the graph of the natural logarithm and how it behaves as you get infinitely close to 0 from the right, okay, because you have a positive there. So let me just sketch the natural logarithm function for you real quick. This is just a sketch. It's not perfect by any means. So the natural logarithm function looks something like this, okay? So this is 0. If you're approaching 0 from the right, what happens to the ln function? Notice how it gets lower and lower, it gets close to negative, it approaches negative infinity, okay? So it's 0, so this basically tells you that the natural logarithm of a really, really small positive number is negative infinity, okay? I know most of you already know that, but I just wanted to state it again. So you're going to have negative, the natural log, negative, the natural logarithm of 0 from the right is negative infinity, right? Of negative infinity, when you multiply these two, you have infinity, okay? So what does this tell me? Well, it tells me that the limit does not exist, right? The limit does not exist. So the limit does not exist. Does not exist. What does that mean? That means the integral diverges. Okay, the integral diverges. There is no area. There's no numerical value that you can assign to this area because the integral diverges. Okay, and let's just write this out. The integral from 2 to 3 dx over x minus 2 has no value. Okay, so there you have it. So I want to thank you so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking here so you can get all these sort of cool calculus clips such as this. Please like this video if you liked it, and I would appreciate if you can post a comment down here to tell me what you think. More videos coming from mathrm.com. Thanks again and have a wonderful day.